Hey. All right, hi everyone, welcome to week 4, and we might talk about assignment 1 since I've just handed it out. Assignment 1 is the database design, data warehouse design assignment, and consists of a case study, and we're going to ask you to design a multi-dimensional schema for a database. So we're asking you to do a logical schema, perhaps with some physical aspects to it. Some of the physical aspects we're actually going to cover this week, but the main intent of the schema that you're going to come up with is as a logical schema. So you'll identify a dimensional model to solve the case study which is attached to the assignment, and you'll then create a star schema based on that dimensional model. You'll need to document the model with a narrative overview. So for those of you who've done 9003, you should be fairly familiar with that kind of concept of a text-based introduction to your model, and a data dictionary. Now, for those of you who did 9003, I can see you freaking out about data dictionaries, because that's fine. I'm looking for a very cut-down data dictionary, not as detailed as we had for 9003. So basically just a short description for each attribute and table in your dimensional model. It might be worth also including in the data dictionary where the source for that data in the schema comes from as well. So the case study that you're going to be designing for is for an organisation called Artworks. There's a background starting on page 4, description of the sort of business requirements and the need for a data warehouse over pages 4 and 5. You'll go through that design schema. As you're reading through, you'll notice that there's 3 source systems which are identified that hold transactional data for the organisation, and they'll be the source systems for your warehouse. So in the data dictionary, it might be a good idea to identify for each attribute where the data for that attribute comes from the source systems. Now, it might be that it comes from several source systems, so I'm not looking for a technically complete description. Just a text-based description would be fine. So it's just a very cut-down, informal version of a data dictionary rather than the complete thing. Now, the case study is there for you to read through. It's spread over 2 pages. There may be more details that you need to do your assignment, so we're making the clients available to you via the Moodle discussion forum. So I'll be playing the role of the client, pretending to pass on your questions to the client and then passing back the answers that they provide to you. So there's 3 different clients that you might ask questions of. So when you're asking a question, address it to the particular person that you want to would like an answer from, and I'll pass the question on for you. But that way you can get more information, and it simulates a bit more realistically the kind of environment in which you do go through and do a design specification. Okay, so the details of submission, it's a 20% assignment, so it counts for 20% of the overall grade, and it's due in week 9. So that's the week after the semester break. So, yes, the semester break's between week 8 and 9, isn't it? Okay, good. So it's the week after the semester break. We're asking you to submit spiral-bound hard copy. Does anyone not know what spiral-bound means? Okay, so I'm sure you've seen it before. It's just that plastic cone binding that's sort of along the left-hand side of the document. You can get it done for about $2 at the Student Service Centre or Officeworks or places like that. What's spiral-bound? Sometimes referred to as cone-bound. But it's just that plastic spiral stuff that they put on the side to keep it all together. You usually get a clear plastic front and a sort of coloured plastic back to it. So we're asking a certain amount of professionalism in the presentation. I don't want just a staple in the top right-hand corner. Now, the case study specification refers to these 3 systems and says that the schemas are attached to the case study. I didn't get a chance before today to finish the schemas, so I apologise for that. The schemas will be available via Moodle very, very soon. I didn't want to hold up handing out the case study and the assignment just for the 3 diagrams, but hopefully they'll be up by the end of today, and I'll send out an email to everyone to alert you to the fact that they're available. But for the moment, you can start making notes, start planning some of the design based on the case study material that you've got there. Any questions that you might have? The deliverables, what you have to do in the deliverables are listed in the specification, the assignment spec, and the assessment criteria that we're using is also included in the assignment specification. The actual marking guide that we use, the tutors will use to assess your assignment with the criteria and the sort of exemplars for the different grade levels against those different criteria will be made available via Moodle as well. So you can have a look there to see exactly what we're looking for.
Is that due the week after Easter?
Yes, that's right. So it's
the first Monday.
Yeah,
Monday?
That's right. The first week back after break. Yes.
Are you sure about that? Because the model says okay.
Yeah, no, I pushed it back to week 9 because I've released it. I wrote Moodle, I wrote this, so I can contradict myself. I've decided to push it back a week. Any other questions? It's due during the lecture. All assignments must include an assignment cover sheet, as per usual. Please make sure you've got the right tutor name written on the assignment cover sheet. Because if we're submitting in the lecture, I need to be able to hand it out to the correct tutor. So please make it sure it's the tutor that you're allocated to, not necessarily the tutor of the tutorial you're attending. Because I know there's a few people who swap classes, but the tutor that you're allocated to is the person who's going to be marking your assignment. So make sure that that's clearly marked on the front. Okay, any other questions about the assignment? No? Okay. I just want to draw your attention to the late submission procedure, the plagiarism and collusion information. Please read that. Please don't plagiarise. Please don't collude. This is an individual assignment. It must be your own work. Can't share your work with others, etc., etc., etc. Please read it. Okay. I'm going to try to fit into at the moment there's no space in the tutorial schedule, but I'm going to try and fit in some space in the tutorial schedule before the Easter break for you to sit down with your tutor and go through some of your design ideas and discuss the assignment with the tutor. So there should be plenty of chance for feedback via the Moodle discussion forums as well as with your tutor in class. All right, let's kick off with the lecture material. So this is week 4. We're going to look at some of the more physical sides or aspects of modelling dimensional models within a relational database environment. So essentially finishing off the last 4 or 5 steps of Kimball's design process that we didn't look at last week. So last week we looked at basic star schemas. Well, we started off by looking at basic dimensional models, and then we moved into star schemas as a way of implementing a dimensional model in a relational database environment. So keep that distinction clear in your minds too. A dimensional model isn't necessarily a star schema. A lot of people do confuse the two things. A conceptual dimensional model can be implemented in lots of different ways, including in a specialised multi-dimensional database management system, so a so-called ND-DBMS. Rather than just a relational database management system. So we're specifically talking this week about star schemas and how you implement star schemas, so the relational kind of approach. We're going to cover a couple of different issues. First of all, we'll do a quick recap of last week, just to refresh your memories about star schemas. And then probably the first half of the lecture or so, we'll be looking at some sample designs from Kimball's textbook. So Kimball's probably the strongest advocate of the dimensional modelling approach, or the star schema-based approach for data warehouses. Even though the dimensional view of data is the most commonly presented at the delivery system end, remember that we can actually choose to implement that dimensional view in the database management system itself, the data warehouse, with, for example, a star schema, or we can map onto a third normal form ER-structured data warehouse with the delivery system with some middleware, and create a sort of on-the-fly dimensional view of the data. So what we're talking about specifically this week, last week and this week, is putting it in the data warehouse itself. So we'll have a look at some of those sample designs from Kimball, just to give you a bit of a feel for different kinds of approaches for different kinds of business problems using a star schema-based approach. And then we'll have a look at 3 specific issues to do with design decisions around handling special kinds of dimensions, so heterogeneous dimensions, what happens with data that changes in the dimension tables themselves, and we flagged that a little bit last week, and how we go about physically storing summarised or aggregate data, because that can pose some physical challenges as well. So we'll look at a few other things to do with dimensions, some design issues that need to be handled, and that should bring us up to the end of the lecture. By the end of this lecture and by the end of the tutorial, you should have all of the skills, at least all of the knowledge to develop the skills to be able to do assignment 1. Okay, off we go. So just to refresh your memory, dimensional modelling, it's a popular approach to structuring data for business intelligence and decision support. We can choose to implement it in the data warehouse, and when it's implemented in the data warehouse, very often it's implemented using a relational database management system and the star schema-based approach. Star schemas consist of a centralised fact table, and as we saw from the tutorials last week, the bulk of the data tends to sit in the fact table. The fact table can be often gigabytes or terabytes in size, whereas the dimension table's generally a lot smaller, maybe kilobytes or megabytes in size. You might have, say, 100,000 records in a dimension table, but you might have millions and millions of records in the fact table. Of course, all of that depends upon the granularity that you choose. Does everyone remember what I mean by the term granularity? Better question is, anyone not recall, does anyone want me to talk about it again? Granularity is one of those design decisions you'll need to discuss in the narrative overview of your assignment 1. So if you're not clear on it, it's important. Okay. So granularity is important. Fact tables, dimension tables. The primary keys of the dimension tables become the primary key of the fact table. That speeds up and simplifies the select statements, the where clause, and allows us to run lots of different kinds of reports very quickly and very easily. We looked at Kimball's steps in the design process, specifically, exactly 9 steps in Kimball's design process, and we looked specifically at the first 5 last week. So we're going to cover kind of the last 4 or so this week. Happens in the design phase, but of course affects just about everything to do with implementation and use of the warehouse and, of course, the delivery system as well. And whilst I don't have an arrow here, this is the ETL process. Of course, the design of the data warehouse is going to impact the ETL process too, so don't forget that. All right, here's a star schema, and you can see the primary keys of the dimension tables making up the primary key of the fact table. Why have we got more than one attribute? More than one non-key attribute in the fact table? What do they represent? Measures, exactly. So what is a measure? How's it different to a fact?
It's going to be some sort of aggregation.
Maybe, not necessarily. It could be a transaction level measure. Yeah, well, that's true. Anyone else be able to tell me the difference between a measure and a fact? It's kind of a trick question in that measures are facts. It's just that there's different ways of representing those facts. So in this case, our facts are sales, and you can see that from the name of the fact table. So we're recording the fact of a sale. But there's different ways of measuring sales. So in this case, we've got two. We've got dollar sales and unit sales. Same fact, just different numbers representing that fact. So dollar value versus the actual quantity of units actually sold. So the attributes in the fact table, the non-key attributes, are generally measures of those facts. Sometimes we also put in the fact table attributes that you would sometimes actually put in, or if you're not modelling this normally using an ER modelling approach, might actually make an attribute of one of the dimension tables. And in my tutorial we came across that situation with product price with one of the exercises. We decided to put it, or I decided, after convincing my class that it was the correct thing to do, put product price in the fact table. Does anyone, perhaps not from my class, have an idea why that might be a good idea? It has to do with the time dimension.
Well, price varies.
Price will change over time, exactly. So if we have price as an attribute of product and the price changes, then that changes the historical record of the price over time. So if we ran a report for, say, 2005, then and we had today's price in the product table, then the prices would all be wrong. In fact, that would perhaps throw out dollar sales, depending if we weren't physically storing dollar sales and we're only calculating on the fly, that would produce the wrong number. So one way of handling that changing data in the dimension is to actually put price in the fact table, and the time key then, or the primary key from the time dimension, then allows us to keep that history over time quite nicely. We're going to look at a couple of other ways of doing that, a couple of other ways of handling changing data in the dimension tables without putting it into the fact table, but we'll get to that later. So that's a fact table. That's a star schema with some attributes. This is Kimball's design process. We kind of got to step 5. This week we're going to look at issues around number 6, so changing data in the dimension tables, number 7 as well, and a few other aspects of physical storage, such as heterogeneous dimensions and so on. And I'll explain what that means when we get to it. We won't talk too much about 8 and 9. We did talk about those last week. So 8 is very similar to the granularity decision. Has to do with how much data you're keeping in the data warehouse. The more data you've got in the data warehouse, the slower the queries run, because there's more data to traverse to find specific pieces of information in the warehouse. So you can very easily improve the performance of the entire sort of business intelligence stack by reducing the size of the data warehouse. And one way we do that is by storing summarised data, so choosing a more coarse level of granularity. Another way of doing that is by archiving off older data, based on the premise that more recent data is probably more often relevant than older data. Now that's not strictly always the case, and you have to be very careful about that. And certainly we don't want to permanently delete the historical data, but if we're frequently archiving off the old data and then bringing it back in because someone's using it in queries, then we perhaps need to readjust our approach to handling that or storing that historical data. Another thing we can do is actually have a coarser level of granularity for older data and a finer level of granularity for more recent data. Again, allowing us to reduce the size of the warehouse, but still having that balance between more recent information, which is probably going to be requiring a finer level of detail, versus more summarised older data. Number 9 has to do with the frequency that we run the ETL process. So remember, the ETL process takes data from the source systems and loads it into the data warehouse. I'm going to get Steve Remington to actually give a short guest lecture in about week 7 or so, talking about the ETL process. But the ETL process doesn't have to run all the time. In fact, generally it runs overnight or over the weekends, maybe even once a month. So that you don't have to have it running every time. There was a movement a couple of years ago called real-time data warehousing, or just-in-time data warehousing, where updates to the source systems would flow through fairly quickly, fairly immediately into the data warehouse. I think I talked a little bit about it in week 1. And I've never really seen a good justification for having to do that. It's certainly possible to do, but the complexity and the cost associated with getting that frequent real-time update to the data warehouse very often isn't justified from the benefits to decision-making that managers actually get from it. Okay, so really this week we're focusing on 6 and 7. So there's a few different issues in there. But before we do that, let's have a look at some more designs. The reason for this is that it exposes you to a few different design ideas. Design patterns are a good thing when you're a designer because it means you don't have to reinvent the wheel every time you come across a new business scenario. And it's based on the idea that most organisations have fundamentally the same kinds of business processes. There may be variations and differences, and you need to tailor designs to each organisation, of course. But fundamentally, selling a product is the same whether it's a supermarket or a retailer or a wholesaler. The basic conceptual process of selling something is fundamentally the same. Likewise, inventory is something that's fairly common to a lot of organisations. Payroll information. This is why a lot of organisations can use the same transaction processing systems, for example, SAP, things like that. So, exposing yourself to different design principles, different design ideas, allows you to become a more flexible designer. So these examples come from Kimball. There's a few other books out there as well. Adamson and Venerable have a book called Data Warehouse Design Solutions, book basically full of just different design solutions. There's there was a movement which I now think is a little bit defunct. I'm not sure how active it is anymore, but I'm pretty sure their website is still up, called Common Data Warehouse Meta Model. And the intent there was to come up with generic models for businesses that can be taken and used for data warehousing. Okay, so we're going to look at inventory, shipments and financial services. Straight from Kimball's book. Different kinds of business processes, but common to lots of different organisations. So let's have a look at inventory first. So inventory management systems are systems that sit in the supply chain between the manufacturer and the retailer. Now, the inventory system may be part of the retailer's organisation, or it might be part of the manufacturer's organisation, or it might be a complete third party. But the idea with inventory is that it can be a fairly mechanical process, but if you can tweak your supply chain to get a small savings per unit that you push through that supply chain, because you're getting lots and lots of units through, that small reduction per unit actually equates to some fairly significant savings. So organisations are frequently looking to improve their supply chain, make it more efficient, and get products through that supply chain more effectively. And there's a whole lot of competing factors there. There's the costs of actually moving products around. Inventory is more specifically focused on stock that's sitting in somewhere like a warehouse and things like that. So in addition to the shipment cost, you've actually got issues around having the real estate on the shelf space, the actual physical space to store products in a warehouse. You want to minimise the amount of real estate that you need for your warehouses, but likewise you don't want to run out of stock. So there's a fine balance there to be made. So inventory management, supply chain management, these are real very specialised fields that can actually deliver significant value to an organisation. It tends to be fairly dry kind of analysis. Oh, there's that airlock thing happening again. Hopefully it'll stop soon. Fairly dry sort of analysis, but the specialists in that field can actually, if they can get small amounts of savings per unit, as I said, that ramps up very quickly. So a common thing in organisations to do is to build some star schema models around inventory. So we're going to look at three different aspects of inventory management and three different star schemas that you might have. As I said, these come all from Kimball. So one model that can give insight into the sort of inventory management for an organisation is what Kimball calls an inventory snapshot model. Basically, looking at stock levels over time and seeing how they vary, because that allows you to make decisions around economic reorder quantities and things like that. So, very simple model. The only measure we've got is quantity on hand, but that's broken down by product, warehouse, and of course time. Now, time is one of those dimensions that should always be on your model. So generally, you start with time and then work out what else you've got. But fairly basic model, but actually quite powerful. Allows you to analyse quantity on hand by product over time. You can look at the performance of different warehouses by time. You can compare different time periods to each other. You can look for seasonality, things like that. So fairly simple. Of course, you go on to complete the attributes of the dimension tables as well. But that's a very simple model, but it actually delivers quite a significant amount of value. It allows quite a few different insights into the inventory management issue. The other aspect of inventory management is the idea of products coming in to the warehouse, so shipments, so handling suppliers and so on. So this is similar to the previous model, but here we're adding in vendor information or supplier information. So you may have difficulties with a particular supplier, and this model allows you to identify that. So you're not just looking at products and warehouses. Now we're analysing shipments by vendor. But of course, shipments are more than just simply having quantity on hand. We're looking at material coming in, and the reliability of vendors is related to not just whether they deliver product on time, but also the quality of those products. So how many returns do we provide? Do we send back to vendors because of faulty products and so on? So Kimball's taken the approach here of adding in some extra measures with regard to inventory from vendors to the point of actually tying the warehouse model back to the primary key of the transaction processing system. So you'll notice that purchase order number and purchase order line item number is included in the fact table. Now, it's not part of the primary key for the warehouse because we still want our star schema to perform as a star schema. But by including the primary key values there as from the transaction processing system as non-key attributes, it does allow us to do reports on inventory. And if we see an anomaly, a problem, we can actually track it back to the source system and follow that back. So that's something that's quite commonly done. But of course, that depends upon having a transaction level granularity. So there is a design trade-off there. We wouldn't be able to summarise the fact table or aggregate the fact table physically in the warehouse if we were to do this. But you notice that there's also the information about the shipment itself, so when it was received, how much was received, how much was inspected, how much, and from that we can derive how much was sent back, and so on. Any questions about that one? So fairly similar to the simple inventory model we had a second ago, but this design idea of tying back to the original source system can sometimes be quite useful. Okay, now inventory of course is more than just shipments coming into a warehouse. Of course we ship stuff out of the warehouse as well. So one useful perspective on inventory management is looking at stock from a transaction kind of perspective, things coming in and things going out as well. So here we've got a transaction dimension, whether it's a shipment coming in or a shipment going out. So this is allowing us to analyse everything that affects the inventory, not just shipments coming in. So we've got, again, purchase order number for both vendor and customer shipments. You might also add in here the vendor and the customer as dimensions, although then you'd have to handle a sort of a dummy customer and a dummy vendor for the different kinds of transactions. So if it's a shipment coming in, then you have a dummy customer, no customer perhaps, or if it's a shipment going out, then you would have a dummy supplier perhaps. Anyway, there's different ways of modelling that. You may actually split the fact table up and have two separate models for shipments and coming in and shipments going out. Okay, so that's inventory. This is what you might have if you were tracking just shipments going out specifically. So where the product leaves the company, delivered to a customer. Each shipment going out, of course, has an invoice attached to it usually, or a purchase order from the customer. And the idea is that each invoice has perhaps a number of different products or stock keeping units on it. So this is Kimball's shipment model. So you can see the fact table here attached to a customer dimension, so who it was shipped to, where it left from, so the warehouse that it was shipped out from, the shipping mode, whether it was sea, land, air, whether it was done via a courier company or whatever, the product, the time. There's also a deal dimension there, maybe customers being given a discount for a bulk purchase, something like that. So by having that deal dimension there, you can see what the impact is on shipments when you've got deals versus no deals. Deal or no deal? Yeah. In the fact table, again, we've got lots of non-key attributes, including tying back to the transaction processing system. So we've got invoice numbers and invoice line items, the order date, and so on. And we can use this to see how much was actually shipped. Oops, what did I do there? So we can see how much was actually shipped, the price that the customer paid, how much the deal was for us, the anticipated arrival date versus the actual arrival date, so we can track performance of our shipping and so on. Just showing some of the attributes for the dimension tables. Remember last week we talked about the grocery chain dimension model, and we talked about adding in extra attributes or trying to anticipate the kinds of questions that our users would have by putting in attributes into the dimension tables that allow different kinds of analyses. So here we've got customer information, but we've also got sales team information a bit attached to the customer. So we can analyse performance of sales teams with regard to shipments. There's in the deal information, you can see there different aspects of deals that we can analyse the fact table by. Now, whilst it's possible to analyse the fact table by some of these different attributes, doing so is not as easy as analysing by the actual deal itself or the customer itself. So for example, if we wanted to analyse by sales team, so if we wanted to look at shipments for a specific sales team, we would have to find all of the customer and the shipped to keys, the primary key values for that sales team. There might be quite a few of them, and then run that against the fact table. And that can be a little bit inefficient. If that kind of reporting happens frequently, it makes sense to convert that dimension or create from that dimension what we call a mini dimension or a degenerate dimension. We'll talk about that later in the lecture. But essentially the idea is that we would take the sales team information out, create it as its own dimension, give it a primary key, and attach it to the fact table as well, so that we can then analyse the fact table by a sales team primary key instead of just the customer primary key. So I'll show you how we do that down the track, but it allows us to slice and dice the fact table a little bit more easily. Okay, so that's shipments. Any questions so far? Yep.
In the fact table, the date information can be separated to another dimension because, as we mentioned before, the non-key attributes are mostly those measures for the fact. So in this case, it involves like the 4, 5 day information, which is we may need use for measures.
Well, they're in the fact table because they're of some relevance to the users. So you can't just say we're not going to have it, and you can't just say in this case that we can attach it to the time dimension, because they're different time-based pieces of information. They're not just the chunks of time that we're grouping the fact table by. So the expected shipment date is going to be different to the expected arrival date, and that may be different to the actual arrival date. So we can't just get rid of them. We need that information there. It's also handling time differently to how time is being handled in the time dimension. So in the time dimension, what we're doing is we're creating chunks of time. So essentially what we're doing is we're turning it a continuous variable, which is time, that well, it doesn't vary, it proceeds at a fairly steady kind of rate. And we're turning that into what's the word? I've forgotten the word. Continuous and discrete, that's it, a discrete variable. So we're basically chunking time up into pieces in the time dimension. So the time key, which is actually missing from my, there's an error in my diagram. There should be a time key in there as well. So my time key chunks up the fact table by these chunks of time. However, these attributes here, the date attributes, are dealing with time as continuous variables. So it's saying the date on which the order for which this row in the fact table occurred is this date. The date on which it arrived is this date, not just the chunks. So actually we can't just rely on the time dimension to do the kind of analysis that those attributes allow us to do. Does that answer your comment? Address your comment? Or okay. All right. Let's push on to financial services then. So most banks have got data warehouses, most insurance companies have got data warehouses and things like that. Imagine this scenario. Imagine there's a large bank. They've got these kinds of different financial services offered to their customers, so a checking account, a savings account, mortgage loans, investment loans, personal loans and so on. And they want to actually be able to market more effectively to households. Now, this is a very common marketing problem for banks. When you open up an account with a bank, you give your personal information, and you might have a joint account with one other person. But there's no easy way for banks to identify which people belong to a household. So their products are set up for individuals and maybe pairs or small numbers of individuals holding their products. But very often they want to market to an entire household. So one way of being able to do that is to analyse the postal address or the residential address of the customers. But that's an imperfect way of grouping customers together as a household. You might actually have several households under the one roof. You might have the one household living in a couple of different houses, perhaps. There's no neat, easy way of doing that. So in many banks there's this dilemma of how they've structured their products versus how they want to market those products. So they want to be able to, imagine they want to market more effectively to households. So what they want to do is build a data warehouse that groups their customers according to some algorithm that they come up with to be able to group households together, and then use that as the basis for marketing their products. Imagine there's 5 years worth of monthly data for each account. Current month has to be a snapshot of the previous day, so that impacts the design of the ETL process, which means that the granularity is probably going to be monthly. The ETL process, though, needs to run every day. So the current month has to be a snapshot as of the previous day. That means that the ETL process, the data warehouse, has to be refreshed overnight. They want to be able to group and compare primary balances across the different accounts, across by household and by account. The key problem, though, is that each account type has different attributes and different facts associated with it. So it's not a simple process of simply saying dimension, account, fact would be, say, balance at the end of the month. There's different attributes and different aspects of each account that we need to keep track of. So that creates a bit of a dilemma for us. And this is getting into what I referred to earlier as heterogeneous dimensions and heterogeneous facts. We'll lead up to it. I want to set the setting first, though. Okay, so each account belongs to a household, and the addresses and things like that may differ from account to account. So we need to rely on some process in the ETL process to group accounts together as households. So the marketers are obviously going to be interested in demographic information and activity on the different accounts so that they can tailor their marketing message appropriately. So let's start putting together a dimensional model for this scenario. And again, this comes straight from Kimball. And this will lead us into this issue of heterogeneous facts and dimensions. So, choosing business process, this is step one in Kimball's process. Identify, we'll take monthly account balances, and that leads us into the granularity decision. So, balance of each account by month, perhaps by branch as well, although accounts and branches kind of go together. And then select the dimensions. And if we do that, we end up with a basic model that kind of looks like this. So we've got account, we've got time, we've got household, and even though accounts belong to or reside within households, we're treating them as two separate things. So in a standard ER model, we might create that relationship between the two dimensions, but because we're specifically interested in the household facts, we've got that relationship between accounts and households going through the fact table. Okay, because the primary keys have to be unique. So we can look at the fact table and work out which accounts belong to which household through the fact table. We've got an account status there. You can tell I've gone through my diagrams with a very fine-tooth comb. The product up the top is the account type, really. It's obviously not shipment. So ship mode key is quite wrong there. It should be product key, obviously. So you may want to change that. Okay, so let's choose the measured facts. Well, we'll go with a couple of simple ones. The primary balance is probably the most obvious measure of this fact table. Another one often worth having is the transaction count. So how many transactions occurred during that month on that account? Because that gives you a good feel for the different usage patterns that different householders have on their accounts. Now, if we go through and complete the dimension tables, you'll notice we've got a couple of attributes there for account, but we're not differentiating between check accounts and savings accounts and loan accounts and things like that. We've got product and product type and category, but we're not taking into account the different attributes that belong to a checking account, like say an overdraft limit that you might have on that account, or a credit limit on a credit card, or the interest earned on a savings account, those kinds of things. So that's missing from this generic kind of dimensional model. So how do we go about incorporating that information into our model? Well, this is where heterogeneous dimensions come in. Heterogeneous just is the opposite of homogeneous. Homogeneous means everything's the same. Heterogeneous means everything's different. Can I get a volunteer, perhaps, to go and jam that door open for me? Thanks, Sylvia. I think there's a bin just next door. You can sort of squirt around. So heterogeneous just means that the different members of the dimension don't have the same pieces of information about them. And it might be that they have different facts or different measures. Thanks, Sylvia. Or they might have different attributes in the dimension table itself. Now, one way of doing that is simply listing all of the different attributes in the dimension table and all of the different measures in the fact table, and allowing some of them to be null for different instances. So, for example, overdraft limit might have values for a check account, but when we've got a savings account, overdraft limit is null. So that's one way of doing it. So logically, we could design it as a single fact table with a single dimension, but we may end up with dozens and dozens of attributes for each different type of account or type of product, and that can lead to complexity and confusion for the end users. And it might also lead to accidentally including certain types of accounts in queries where you didn't intend to include that information. So this is how it might look if you had everything in one table. Everything in one dimension table and the corresponding fact table. So you'd have all your different checking attributes, all your different savings accounts attributes, and so on, and likewise with the measures in the fact table. So you can imagine your tables get very, very big, and you're going to end up with lots of empty spaces in those tables for each product, each specific product. So physically, that creates a real problem for us. So you might end up with hundreds of attributes in these tables. Creates cost in terms of disk space, depending on the database management system. Some DBMSs don't leave space for null values on the disk, but some don't. Speed and complexity becomes an issue as well. So constructing your queries becomes more difficult. Mistakes are easier to make. So one approach is to actually split these up into separate fact tables for each different kind of product or dimension member. Now I've got there another job for metadata. That comes. I've obviously reused this slide from a different presentation. But metadata allows us to map the physical split of these separate separate products and fact tables, so that from the user's perspective they see only one unified structure. But physically we can more efficiently store the different bits of information. So this is how it might actually look. So you end up with 2, 3, 4, 5 different versions of the schema with different focuses. Up the top left here, we've got the attributes and the measures that are common to all of the different products. So what we call the core facts and the core product table. And here we identified primary balance and transaction count. But you'll notice that we don't have those specific product-specific attributes and measures. Instead, we have another copy of the fact table that has the same primary key structure as the core fact table. So if we were to do it as an ER diagram, there'd be a mandatory one-to-one mapping between the core fact table and the customised fact table. We create a different fact table for each different kind of product. And in there, we put in the specific measures for that kind of product. And same with the dimension table. So we have the specific version of that dimension table for that kind of product with those saving attributes. Same primary keys in both, so we can very easily go from one table to the other because the primary key is the same. It's, like I said, it's a mandatory one-to-one be optional at one end, but it's a one-to-one relationship between the tables, so the rows can logically line up. But it allows us to avoid storing empty space on the disk, avoid storing nulls and things like that. And when we're doing queries about, in this case, savings accounts, we can hit the savings fact tables. If we're doing stuff that's common across all accounts, we can hit that fact table up there. If we're doing checking accounts, well, we'd hit the customised check fact table, and so on. Does that make sense? Okay, so the key to this working is making sure that the primary keys are the same. All right, if you can wrap your minds around that, that's a good thing. All right, let's have a look at another issue, mini dimensions. So I mentioned earlier this issue of when you've got a denormalised dimension table, often you've got hierarchical structures within the dimension table. So before we had customers and sales teams. So each sales team probably has many customers if you were going to normalise it, but we denormalised into a single table. Often we group customers together according to their demographic information, or we might group product information together according to their product group, category, department, brand, and so on. So dimensions often have these hierarchical structures in them. Time, for example, is a very common one. That's fine from a denormalised structure if we're frequently doing queries at the bottom level of the hierarchy. So if we're often running queries about specific individual customers or individual products, then the fact table, that dimensional structure works pretty well. But if we're frequently doing queries on higher levels of that dimensional hierarchy, so if we're doing lots of analyses by product type or customer group, then that means we're frequently running queries with multiple primary key values in the where clause, because the primary key is allocated to the individual product or the individual customer. We're using product key, customer ID, and so on. So the number of customers within a particular product group, say it's 100, if you wanted to analyse by that product group, then we'd be querying the fact table according to 100 different customer IDs, which is certainly possible to do, but it's not particularly efficient. Much easier is to allocate a primary key to that thing that we're analysing by, in this case product type or customer group. So giving each of those their own primary key. Now the way to do that is to create what we call a mini dimension for that hierarchical group. So here's an example for demographic information for a customer, so one of those common groupings. And what we've done is we've taken the demographic information out of customer So it's not that we've strictly normalised things, but we've taken that group of data out as a separate kind of dimension. It's not its own dimension, certainly, but we've allocated a primary key to it, and it now forms part of the primary key of the fact table. So that instead of analysing by 100 different customer IDs or customer keys against the fact table, we can analyse by one single demographic key instead. And that makes the query run a lot faster. Notice that there's also a relationship there between demographic and customer. So we can still work out what demographic grouping the customer belongs to. So it's a one-to-many relationship. You notice the demographic key is a foreign key in customer. So we've still got that relationship there. And it is kind of normalised, but we're not snowflaking here. We're doing it specifically because the users are frequently doing analysis by demographic rather than individual customer. And we're speeding up those queries by creating this mini dimension. So Kimball sometimes calls it a degenerate dimension. Sometimes it's referred to as a mini dimension. So it's not a full, complete dimension in its own right, but it's a bit of a dimension being pulled out to make querying the fact table a lot easier and a lot faster. So that's mini dimension stuff. This may be something that you decide to do in the assignment. It may not be. Yes?
Is this kind of separation done in the ETL process? In the ETL process, it would be very good.
Well, this is the database schema. So this is the structure of the data warehouse. The ETL process, because it's loading data into the data warehouse, is completely dependent upon the structure that you choose. So if you're structuring your warehouse according to this structure, then absolutely the ETL process has got to load data into that structure. What you often find is that you create mini dimensions after a while of using the system, so seeing which reports get run most frequently, and you're trying to think, well, how can we speed up the performance of the warehouse? One way is to split that dimension table up into create a mini dimension, but it does have consequences, of course, for the ETL process. You have to redesign the ETL process to handle that. But usually it's not too hard to do because there's quite clear groupings typically. A single table with a single dimension table with a composite key. It wouldn't be a composite key. Oh yeah, I suppose it would be. Yeah, that'd work. I think. Yep. The problem with that is that if they're frequently analysing by, in this case, demographics, the users are going to be looking at a table for that demographic information, and if they're hitting a customer table instead of demographic table, that could be... Yeah, it would be. Yeah, no, look, it's physically doable. I'd have to think through the pros and cons a bit, but yeah, I think it would work. But essentially you're doing the same thing, it's just a slightly different physical representation of that. Yeah. Yes?
So the mini dimension is the concept like we can split some very large dimension table to two separate dimension tables which can facilitate.
Yes, but don't get hung up on the idea that you're splitting up a dimension table. What we're doing is we're adding an extra primary key into the fact table to allow us to analyse the fact table by this primary key. It's not that we're normalising or trying to split the dimension table up because it's big or because it's got lots of data or because we're trying to normalise it. It's purely because the users are frequently trying to split the fact table up according to what would become a primary key value. And we're simply introducing that primary key to make that much easier to do. So the focus is purely on the decision-making and reporting requirements of the users and how they're accessing the fact table rather than the dimension table per se. Yep. So it looks like it's Snowflake, but it's not snowflaking. It's done for a different reason. Yeah, snowflakes and star schemes are kind of the same thing. It's just a snowflake has got a normalised dimension table. But yeah, the reason for doing this is quite different to the reason for doing snowflaking. So the reason for snowflaking is typically the designer doesn't feel comfortable having denormalised dimension tables. They just feel the need, they're compelled to normalise the tables, whereas this is done for a very specific user requirement. Okay, so that's mini dimensions. It's 11 o'clock. Do you want to take a break? Yeah, there's a few nods. Okay, let's take a 5-minute break. We'll come back and we'll talk about slowly changing dimensions. Cool. Well, you know, it's all been recorded. So. Okay, see ya.
I'm trying to find out what people are missing in class.
But it's grouping those things together. So the time dimension is the level of detail the time dimension is given by the gradient index. So how much detail they have. Monthly data is daily data is anything if it's daily data, then the time dimension is is the data. So in transport processes, it's more time scale. This side of the when it is aggregate in the WebAT, you can have an transaction of all the transactions that occur on the day into one single sum. And it will attach to, and all of those transactions will attach to the same time key. Between possibly hundreds or thousands of transactions in one single bit. So it's actually
During the tutorial, Joseph asked me how to the experiment to find out what do you want about the keyboard, you know, the keyboard combination of using keyboard and mouse. Pretty interesting stuff. Very simple entry level stuff. Not very exciting, but I think
Okay, let's get underway again. So we've been talking about some of the physical design considerations when you're doing a star schema-based analysis. So we've looked at the issue of heterogeneous dimensions and heterogeneous facts. It's a hard word to say, heterogeneous. Heterogeneous is sometimes easier to put the emphasis on the different syllable. So we've looked at heterogeneous dimensions and facts. We've looked at the idea of mini dimensions as solving a particular design issue. Keeping in mind that it's not snowflaking, it's done for a very different kind of reason. This is another common design problem that star schema modelers face, is when data in the dimension tables themselves change. So for example, a customer changes their address, product price changes or something like that. Obviously if we simply change the data in the dimension tables, that's changing the data for all time in the data warehouse. So unlike a transaction processing system where we're very often interested in the current version of the current snapshot of reality, with data warehouses we've got that non-volatile, time-variant aspect to the definition of the data. So any change we make to the dimension table is going to change all of history. Any historical reports we run is going to be using data in that dimension table. So one solution, of course, is to simply put the changing data in the fact table, because we've got that time dimension and it very nicely splits up, chunks up the fact table by that time basis. So when things change over time, the time dimension allows us to differentiate between one version of a thing versus another version of a thing. However, sometimes it excessively confuses the issue. So it's not really a universal solution to just put everything in the fact table. So what we're going to look at is 3 different approaches that Kimball talks about: type 1, type 2 and type 3, in how you can structure a dimension table to handle changing data over time. The first one, which is Kimball refers to as type 1, I don't think is really a strategy at all. It's simply to overwrite the data. So there's not much complexity there. It's simply, if the customer's address changes, overwrite their address with the current address. But there's type 2 and type 3 which handle changing data over time so that we don't lose that historic aspect. So type 1, overwrite the data. Easy done. ETL process simply updates the dimension table. Easy to implement, but of course you lose all of that history. Now it may not be a problem if you lose that history, so because it's the easiest to implement, this is the desired solution, I guess, for any data where you don't need to keep that historical information around. And some data might fit into that category. Usually we make these design decisions on an attribute by attribute basis. So this attribute in this dimension table, do we need to keep that historical data around? If not, then we can simply use this overwrite approach to any data that changes there. Okay, but often we do want to keep the data around. And the most flexible approach to keeping that data around is to actually expand the dimension table a bit so that you end up with a brand new record to hold the new data. So we kind of add in a version number to the row of the dimension table, so that as new versions of the customer or the product or whatever is changing get created, we create a new version. Rather than simply overwriting that row of data in the table, we create a new row. So we've got the old row to keep the old data and a new row with the new data. Now, that means we need to change the primary key of the dimension table, because we probably want to keep the primary key that refers to the thing, so the customer ID or the product ID, but obviously we can't have duplicate primary keys, so we need to add in the version number as part of the primary key. Yeah, well, there's a couple of approaches. One is to create a composite primary key, sorry, a concatenated primary key with the original key and a version number, or we can create a composite key with 2 attributes. One is the original attribute primary key with a version number as a separate attribute. Either approach is fine. Might find the fact table works a little bit better if you've got a single attribute rather than multiple attributes with the primary key, but it's going to differ from DBMS to DBMS and the nature of the data itself. So you generalise the dimension key, perhaps add 2 or 3 digits depending on how many different versions you're going to end up having of rows. So you've got to anticipate the potential number of changes, either as a single primary key or, as I said, a split composite key. The advantage is that this automatically partitions history, so it's very easy to track back over time by working our way back through the different version numbers. You might also include a timestamp, the date that it became effective and the date that it ceased to be effective. That may be useful as well in the dimension table. So that allows you to see when the change happened as a timestamp. But because you've got the time dimension in the fact table, you can generally see roughly when things changed in time through the fact table. The disadvantage, of course, of this approach is that it's a lot more complex. With the ETL process, you have to identify what data's changed. You have to create a brand new record. You have to have a more complex key structure as a result. So that can add complexity to the ETL process and therefore add time that it takes the ETL process to run, and that can be an issue. And it creates a slightly more complex data structure as well. So when you start analysing the fact table, you can potentially end up with more complex queries based on different versions of different things. Okay, so that's... one of the other disadvantages is that it may also make your dimension table become really quite large. So if you're creating multiple versions of each row, that means that your dimension table could be 2 or 3 times larger, depending on the number of versions on average per instance of that dimension table you're keeping around. For most dimension tables, that's not going to be a problem. So you might have, say, 50,000 products, and they may change their price, say, once every 3 or 4 years. So you might have, over, say, 6 years, you might have 2 or 3 times the number of records in that product table than you would have otherwise. And if you're talking 50,000 products, you're really only talking, 200,000 rows? Which for a database management system is nothing. That's not a problem at all. However, some dimensions can be very big. So if you're, for example, Telstra, with how many million customers has Telstra got? Let's say, rough estimate, 15 million customers. If you're keeping, say, 3 or 4 versions of each customer, that could become a bit of an issue. You might end up with 30 or 40 or 50 million rows in that table. So that might become an issue. But generally, even for pretty large dimension tables, this type 2 approach is the most flexible approach, and the downside is fairly limited. But if you do find that it's actually too big, Kimball suggests the type 3 approach. The type 3 approach is to address the problem rather than from a row level issue, so creating a brand new row for each changed value, attack it from an attribute perspective. So create an extra attribute for each version of a particular column in the table that you want to keep track of. So for example, you might have a customer address, and you're only interested in keeping track of their current address and the previous address. So rather than duplicating a row, expanding the primary key and so on, simply add in an extra column called former address. So when the address changes, the current address moves to the former address, you put in the new one in the current address field. So the advantage is that this is dead easy to implement. It's not hard, doesn't really fundamentally change the structure of your database, data warehouse structure at all. So if you're implementing it down the track, it's easy to put into a live data warehouse. It's really the easiest approach when you've only got that current and previous version that you're interested in keeping. But of course, the disadvantage is that when the customer changes their address again, the old address pops out and gets deleted. So we're no longer keeping track of that. So that can be an issue, but it's a kind of middle ground between simply overwriting the data versus the full, complete type 2 duplication of a row, of a record in the dimension table. Okay, does that make sense? How do you choose between them? Well, type 1, if you're not interested in history at all, type 1 is the easiest way to go. Simply overwrite the data. Type 2 is the preferred approach if the changing data is not excessively large. And by excessively large, we're talking really, really, really large. So, even dimension tables with hundreds of thousands or even millions of records still cope fairly well with a type 2 approach anyway. Type 3 approach is not as flexible as type 2, so you use it when you've got really, really big dimensions, massive dimensions, millions and millions of records, and you're not interested in keeping that full, complete history. You're only worried about 1 or 2 versions of history. Okay, so any questions? Yep. Yep.
Yeah, as you mentioned, there's only one current value and old value.
Yes.
So how we measure, how we keep the archive from maybe more than 3 or 4?
You can't. That's the problem with the Type 3 approach.
So in this case, if I want to keep more than 2 or 3 versions, I need to use the Type 2, right?
That's right. Yep.
And
You can always keep adding columns if you like, but it's not an ideal situation. No. It's really you've got to make a decision with the Type 3 approach. You've got to be realistic. Okay, we only need to keep 1 or 2 versions, and probably customers' addresses. That may be that kind of thing that you'd be interested in doing. But if it was, say, the product price, for example, then no. Look, you want to keep the accuracy of the prices that products were sold at for the entire history of the data warehouse. So you'd never use a Type 2 approach for product price, for example.
okay, another question is it common the case that usually the architecture or the designer align the archive method for the whole system they decide, or we can use different archive method for different dimensions?
There's nothing physical that would prevent you doing different archival methods for different dimensions, but look, it depends on a whole range of things, organisational policies, what their approach to archiving their data is, the complexity of bringing back an archive and making it live again, the complexity of the archival process itself, the features of the DBMS, for example. So the easiest way to archive stuff is to actually just do a replica of the database. So to copy the whole thing and use the database management system's replication features to create that archive for you. But yeah, look, the answer to your question is it depends on a range of factors. Yeah.
I want to go for the third type of third method.
Yep.
Because it's creating a new column is involved. So should this column be usually designed within the design method? Or
Ideally, yes. Yeah. So as you're doing the initial design, you should try to anticipate the kind of approach to handling the changing data. So ideally, you'd put it in, but adding a column to a database table is not. It's not an insignificant thing to do, but it's not the hardest structural change that anyone's ever made to a database schema. It's a fairly common occurrence to add in a column. It's less common or it's harder to take away columns because you're losing data, and it may affect the structural integrity of the database. But if you're adding a non-key attribute column and you're happy for it to contain null values, so you simply create the column. It's very easy to do, very quick. It's one SQL command. Much harder to do is to change the primary key. So if you're going to introduce Type 2 after you've gone live with the data warehouse, that is harder to do. Not impossible, but might require having the data warehouse offline for a while. Yep.
In case of Type 2, like we said that we'll introduce a version ID.
Yes.
And it will act as a composite primary key with the product or
That's right.
whichever dimension.
Yeah. It could be either a composite or a concatenated key. You can do either approach. Yeah.
In case if it is a composite primary key, will it flow into the fact table? The
Yes.
version ID?
Yes.
It will.
Absolutely, because the primary key of the dimension table has got to be a foreign key in the fact table.
So both of them have to be there.
Absolutely. If you change the primary key of any table, and this is true of any database, not just data warehouses, if you change the primary key of a table, then any foreign key that primary key appears as also has to change. Yeah.
Do we actually implement differential integrity between fact and the dimension table in data warehouse? Because
So ask that again. Do we implement the?
differential integrity, I mean the relationship, parent-child relationship.
Yeah, absolutely. It's
Because that won't it slow down the ETL process? Because in one of our other units, CRM,
Yeah.
in a tute, the tutor said that normally, I mean, logically there is relationship, but we don't implement it for the sake of.
well. It depends on what you mean by implement. In the traditional sense of a relational database management system, there is no such thing as a relationship. They're simply tables. So later database management systems, certainly the current versions of database management systems have things that features that address the relationships between tables. But still, conceptually, a relationship is not a physical thing other than a primary key, foreign key structure. So if you've got a column in a database and it happens to hold data values that match up to another column in another table, then that's a relationship. Now, you may choose to do some things that enforce aspects of that relationship. So you may enforce referential integrity in the database management system itself, but that's not really part of the relational database paradigm. It's just a feature that database vendors have put into their DBMSs to improve data quality and so on. So whether, I guess by implementation, you're referring to turning on those features, like checking referential integrity and so on. And the decision to do that really depends upon performance. If the warehouse performs adequately with those features turned on, probably it makes sense to do so, because you really don't want poor referential integrity in a data warehouse, or any database for that matter. But if it does affect performance and you can turn it off, then do so. Because remember, the data's being fed in via an ETL process. So a lot of those inconsistencies that lead to referential integrity problems can be automated and solved because it's written in code rather than relying on human data entry operators. Yeah. So again, that's kind of the same answer. It depends. Yeah. And look, data warehousing is one of those fields that, even more so than OLTP systems, you kind of have to have an attitude of, we just get it done. So if it means creating some hacks or sacrificing some of the engineering purity to end up with a functioning system, then that's probably okay. It's not ideal, and I certainly wouldn't go out advocating a cowboy approach to engineering your data warehouse. But keep in mind, a data warehouse is probably going to have a lifespan of maybe 3 to 5 years, whereas an OLTP system we're designing for possibly 30 or 40 years. So we don't have quite the same engineering requirements. The main aim of a data warehouse is to get the right data to the right people at the right time. So we're looking for efficiency, making it run as fast as we possibly can, to handle as much data as it possibly can, to satisfy the right decision requirements of the users. And so the phrase I often use is baling wire and duct tape. You cobble the system together and make sure it runs as quickly and fast as possible. It may require hacking the system, hacking the DBMS, tweaking buffers and different properties of the DBMS, configuration properties, to maximise the performance. Whereas with OLTP systems, it's all about the insert, update and delete anomalies. The same reason we normalise stuff is the same reason we configure a DBMS to be robust and reliable. And we want that for the warehouse too, but it's less a stringent requirement. Yeah. It sounds like I'm advocating for poorly engineered warehouses, and I'm really not. But it's just a slightly different mindset. Yeah. Okay, so type 1, type 2, type 3, it's slightly changing dimensions. Any other questions about that before we move on? We've actually got a little bit of time. Okay. Next thing I want to look at is the issue of handling aggregate information. This is kind of similar to the mini-dimension issue. It's driven by the fact that when you've got hierarchies within dimensions, the different levels of the hierarchies typically refer to different levels of aggregation of fact table data. So for example, in the time dimension we might have day, week and month, and at the day level in the fact table, that might be the base level of granularity in the fact table. Maybe each row in the fact table represents one day. And then if we're analysing by week, we simply sum those days together. If we're analysing by month, we sum the days or the weeks together. So different levels of aggregation. Now, that level of aggregation may be represented to the end user by the delivery system, so the front-end system that they're interacting with. The aggregates may be calculated on the fly. So physically stored in the data warehouse tables might be 7 days worth of data, and the front-end system takes those 7 days worth of data, adds them together to come up with a weekly figure, and does it on the fly. Every time the report is run, it does that calculation. Now, the easiest way to speed up the performance of a data warehouse is to pre-calculate those aggregate summaries, to do that summing during the ETL process rather than at the time that the report is run. The reason for that is no one's using the system when the ETL process is running, hopefully, or at least fewer people are using it. So fewer people notice the processing time to do that calculation. Also, it means that the calculation's done once rather than every time the report is run. So again, that saves on processing time. So aggregates are probably the most easiest, most effective way of improving the data warehouse performance, but we've got to store those aggregates somewhere in the data warehouse. If we're calculating a result, it doesn't make sense to simply throw it away. We've got to store it physically in the database somewhere. Now, there's a few different approaches for doing that. One naive approach, or one simple approach, is to simply create a new member for the dimension. Sorry, member, a bit of terminology. In the BI world, the OLAP delivery system end of the sort of dimensional modelling industry, instead of rows and records in dimension tables, they talk about members of dimensions. So, for example, with a product dimension, you might have all of the different products would be members of the product dimension. In the custom dimension, all of the different customers are members of the customer dimension. For us, we talk about instances or rows in the dimension tables. So one way to store an aggregate value in the fact table is to add in an extra member of the dimension for each hierarchy within the dimension table. So in addition to day 1, 2, 3, 4, 5, 6 and 7 in the time dimension, we might have an 8th special day called all days or all week. We might add in another member of that dimension called all month, and another one for all year. So we add in an extra attribute for each hierarchical level in the dimension. That creates an extra primary key value, and therefore an extra row in the fact table that we can then store the summarised value in. Sorry, that was a poor way of expressing it. So we're creating an extra row in the fact table to store that aggregate pre-calculated value. Okay, so time ID 1 through to 7 might be the first 7 days of the year. Time ID 8 is the total for that first week of the year. And then you move on to time ID 9, 10, 11, 12, that's the second week and so on. And then maybe time ID 32 is the total for that first month. And you keep adding entries until you've got covered the entire data set. Okay, so you end up with something that looks a little bit like this. So here's a product table and a sales fact table. And we've got a couple of different kinds of products. We've got product categories, bins and hoses. And you can see that the first 3 entries in this product table are the individual bin products, so small, medium and large bins. And then product number 4 is all bins. Same with hoses. Product ID 9 is all hoses. So you can see that these aggregated values, product key 4, consists of the sum of the first product ID 3 and 1 added together. Product 3, product 1. Product 1 and 3, yeah. 6 is a 20 metre hose. So the sum for all hoses is 7.5 because it's 7.5 for 6. 28.8 plus 8 is 36. So this row here is the sum of these 2 rows. So it's single fact table, but we've got the aggregate values stored in the fact table. Fairly easy to implement. It just means that we're implementing the aggregate values or the pre-calculation of the aggregate values in the data itself rather than the data structure. So no change to the table structures at all. It's purely just the data values themselves that we're manipulating to allow us to store that aggregate value. Can anyone see the big disadvantage here without skipping ahead in the slides to see what the answer is?
You want to ensure that any sort of aggregation that happens all happens in that process.
Exactly
and
right.
Not at the delivery system, otherwise you're doing it double.
Yeah, as soon as you say select sum bracket dollar sales, you're double counting or triple counting or quadruple counting. So it creates a problem from that perspective. So what's the solution? Well, it's kind of like the solution to the heterogeneous dimensions and facts. We create a separate fact table for each level of the hierarchy in the dimension. So we have at the base level of the hierarchy, the original model that we had. So sales and product. And then the next level up in the hierarchy, we create another fact table, a separate table with a separate dimension table to refer to that category, that next level up in the hierarchy. And then we simply store the data, the aggregate data in that one there. Does that make sense? Perhaps if I show you how that looks in a table structure. So we split the fact tables and the dimension tables according to the hierarchy levels. So now we can very easily do a select sum bracket dollar sales, in fact from either of those fact tables, and get the right answer. The disadvantage, of course, is that we've just doubled the size of our database schema, doubled the complexity of our database schema. You have to do this for every single level of every single hierarchy in every single dimension too. So you end up with dozens, maybe even hundreds of fact tables. So you end up with a really big, really complex database schema. For little obvious benefit to the end user. So all of a sudden their schemas become really, really complex, and the only benefit they really see is that the performance of the warehouse gets better, but it makes it less usable. So the answer to that is a thing called an aggregate navigator. So really, logically, we're still storing the same information. It's still the same single dimensional structure. It's just we're physically breaking it out into its different aggregate levels. There's a piece of software that a lot of database vendors are now including. It used to be that you had to get fairly specialised data warehousing DBMSs that included this feature. But it's a piece of software called an aggregate navigator, and basically what it does is it sits between the end user's delivery system and the data warehouse and parses the SQL that comes from the delivery system tool. So the end user types the original SQL, or sorry, the end user's tool sends the original SQL that would have hit the original dimensional structure. The aggregate navigator scans that SQL and works out what the most efficient hierarchical or aggregate level table structure is to hit to answer that query. If the query is referring to base level data, it'll hit the base level fact table. If the query is referring to more summarised data, it'll hit the summarised table instead, because that's going to be much, much quicker to query. So if I just go back, running a sum against the sales fact table requires adding up 3 values. Running that same calculation against this table gives exactly the same result, only has to hit 2 values. So even though this is a very trivial, very small example, already this thing here runs at 66% of the time that it takes to run that one up there. So it's only 2/3 rather than 3. So the aggregate navigator intelligently, automatically, like a black box, parses the SQL automatically and hits the appropriate fact table to get the results back in the most efficient way possible. Now the only way it will work is if you've got really good metadata that describes the different structures of the tables, how the aggregates work. Not all aggregates are sums. Sometimes it's average, sometimes it's something else. So the metadata repository and the aggregate navigator together try to intelligently guess what the most efficient table structure is going to be to hit with the SQL that's coming into it. It also keeps track of the different user statistics. So it doesn't make sense to create an aggregate level structure if people aren't really doing many queries against that aggregate level structure. It's only when you're getting frequent queries, like the mini dimension structure, frequent queries hitting that level of aggregation, that it makes sense to create that physical structure in the DBMS. But it's a nifty tool, and from the end user's perspective, nothing changes, but all of a sudden their queries start running a lot faster. And from a user perspective, that's actually really quite critical. Performance is, for the front-end delivery system, is perhaps more critical than for data entry systems. So we kind of think of OLTP systems as having to be quite responsive. If you're using an ATM, you put your card in and you type in your PIN, and then it takes 2 minutes to process your PIN. You think something's going to go wrong, you call the bank, you start panicking. So there is a certain performance requirement there. But the consequences of slow performance on the ATM is moderate. With a business intelligence system, though, the consequences of poor performance are that you actually break the train of thought of the end user. And this is kind of getting into the territory of FIT 5093 and 5094. But if we're supporting decision making in an exploratory kind of fashion, we're encouraging end users to explore the information, answer questions, answer one question which raises a whole lot of other questions, and then they go and answer that question, and so on, in an interactive kind of fashion. The kind of mental state, the cognitive state that you want your users to be in is known formally as a state of flow. And this is a psychological concept. It refers to that situation where you become really focused, you become very efficient, you sort of block out the rest of any kind of distractions, and you really get in the zone. Everyone here, I'm sure, has experienced that situation. Maybe you're reading a book or playing a video game or working on an essay or something like that. You get really efficient, really productive because you're really focused. And that happens to BI users as well. As they're answering one question, a thought fires off and they go, oh, I wonder what this would be. And they go off and try to answer that question. As soon as there's any kind of significant delay caused by the user interface, that flow is very easy to break. Once the person's out of a mode of flow, it's very difficult to get back into it. And I'm sure you've all had this experience when you've been in that kind of productive zone, someone comes and interrupts you. It takes a while to get back into that level of productivity that you were in before. Same thing happens with BI. So when the data warehouse takes 2 minutes to run a report, bang, you've lost the flow. And the consequence is that the user forgets why they were running the report. And maybe they were thinking the next 2 or 3 questions down the track as well. And they've lost that train of thought too. So the consequences of poor performance of the delivery system, and by extension the data warehouse, is that you may end up not answering the questions that the decision maker should be answering. So it's really quite critical. So aggregate navigation is one way to really easily speed up performance. Mini dimensions is another way. Trying to shrink the size of the data warehouse, shrink the amount of data that has to be scanned to run a report. All of these things are really critical to getting adequate performance out of the warehouse that contributes then, by extension, to the performance of the delivery system and the level of interactivity and the state of flow of the end users. So it's really quite important. Okay, so this is actually my last slide for this week. What to read? Well, go out and read a bunch of stuff, particularly Kimball's work on, if you're trying to understand mini dimensions, slowly changing dimensions, heterogeneous dimensions, pretty much anything to do with physical aspects of star schema modelling. Kimball's resources are absolutely fantastic. Obviously the books are really useful, and I'm sure some of you have already hit Kimball's data warehousing textbooks. But Kimball's website is also really, really good. There's a bunch of really useful articles that are written by Kimball, as well as a bunch of other consultants who work for him, dealing with specific issues that they've found as they've tried to build a data warehouse, or they've designed a data warehouse for a particular client. They've come up against a design problem and they said, right, well, here's how we solve this design problem. So it's a really good useful resource for people constructing particularly star schemas, data mart type data warehouses, as opposed to large-scale enterprise data warehouses that are very often non-dimensional in their design. Okay, make sure you've read Kimball's Dimensional Modelling Manifesto. That was last week's reading. It's quite short, quite easy to read. And this week, I want you to read Robert Armstrong's Rebuttal to Ralph. I think he literally called it Rebuttal to Ralph, where he argues for a third normal form ER modelling approach. Robert Armstrong's one of the principal consultants for Teradata, and he's very passionate about advocating for large-scale, third normal form ER-type data warehouses. I'm obviously a bit more on the Kimball side than that side, but expose yourself to the arguments. See what they have to say, see if you agree or not. Okay, aggregate navigators built into quite a few different products these days. It used to be fairly rare, but you'll find it in large industrial strength DBMSs like Oracle and DB2 and so on. Okay, we're done. Any questions before you go? It's not my photo, this is a standard Apple stock photography. Any questions before we go? Any questions about the assignment? Anyone not got the assignment spec? As I said, the schemas for the source systems will be made available very soon, so I apologise for not having them to print out and hand them out today. But I will upload them to Moodle as soon as they're ready, and I'll send out an email to say that you can grab them from Moodle. And if you particularly want me to, I can print them out for next week too. How many people would want me to do the printout next week? 1 or 2. I suspect most of you will want to print it off as soon as it becomes available. So I'll do a short print run, maybe of say half the class, and see how we go. But I will let you know as soon as it's available on Moodle. Okay, see you guys soon. I'll see the rest of you next week. Hi. Oh, why didn't you ask them in the lecture? I'm going to ask as we go along.
Stand for the general understanding of the same part or
the rows in this table have a primary key called demographic key, and the rows in this table have a primary key called customer key. There's a primary key foreign key relationship here, so we can work out which demographic group this customer belongs to. But it's a one. Well, yeah, this is a database. This is an ER model. You know ER modelling?
Yeah.
Yeah. So each entity in an ER model represents a table.
So it's a new entity. I know.
Every box here is a table.
It's a.
This is an ER model. So every box, every entity is a table.
เวอร์ชันนี้มันอัพขึ้นมาเยอะเลยนะเว้ย
ใช่ใช่
เขาบอกว่า positive
Yeah.
การปรับความเร็ว
These are ER models.
เพราะว่ามันเร็วอะไรอย่างเงี้ยเร็วเยอะเลย
You've done the ER model. So you know what an ER model is. This is a subsection of the ER model. So there's other tables. This is focusing on one specific part.
This is this table is a new one we create for the. It's already
Well, it might be
existing.
created at the time when you designed the ER, so it may not be new, but it's a separate table to this one. It's a separate table to this one.
It's already exist or different.
I don't know what you mean by already exists, because all of these tables are created by us. We're designing the data records, so we design.
Actually, the tables are designed according to the user's requirements. It's already existed, and if we,
Exists where?
I mean, this table is already. We created a table according to the user's requirements and.
Any design is done in accordance with user requirements. If we're designing something, it's got to be done according to requirements.
So the ER model is designed by ourselves.
Yeah. This is what these two lectures have all been about, designing the data.
If this table exists or not depends on us, or depends on the requirements.
Well, you're a designer, so your design. This is a bit like saying this wall here exists because of the user requirements or because the architect designed the wall. Well, it's both. The architect went, oh, well, we need a wall here because the users want a wall here. So for us, we're designers. We're designing a data warehouse because we're trying to support user requirements. Yeah. And that's the case with the assignment. There's a case study there. You've got to identify what the user requirements are and you design a structure to meet those requirements. So this is an example of one kind of design pattern. One kind of design pattern that we can use to solve a particular design problem where we've got groupings of a hierarchy and a dimension. And it's being frequently used to analyse the data. And if we're anticipating it's going to be more commonly used than the base level of the hierarchy, then it makes sense to take it out as a mini dimension because it will make
Sometimes we type only on the computer, and the next time we type the first letter, then display
No, it's not to do with that. Do you understand the concept of a hierarchy?
Yeah, I understand.
So in this case, we're talking customers and demographic groups.
Demographic is a higher
High level than hierarchy.
yeah.
So a demographic group would consist of many customers.
You can't just say that. It's more of that. So, for example, the subject of data.
Okay, I understand. There are large hierarchies and small hierarchies, like the demographics. Then the smaller is the dress or the.
No, there's only one thing. It's called, the whole thing is a hierarchy.
Yeah, that's for you.
There's levels in hierarchy. So you might have lots of customers
They're working with subject.
grouped into several groups. So that's one level of hierarchy, another level of hierarchy, and you might group those groups together into smaller groups as well, into a smaller number of groups as well. So you might have 1, 2, 3 levels of hierarchy.
Like the organization of a company. There's managers, there are departments, there are members in each department. Oh, I
So that's a single hierarchy.
this hierarchy, but there are different levels.
Different, exactly right.
Okay. Thank
So the mini dimension represents a level in the hierarchy. That's often being used as that table rather than the bottom level of the hierarchy. So when you've got the bottom level of the hierarchy being used frequently, it means that if you're doing analysis at this level here, you've got to use all the criteria you've got to understand here. So you might have 100 people in the group. That means you've got to use 100 keys when you're analysing this level. Whereas if you create it as a mini dimension, this level has its own primary key value. So you're analysing by one primary key value.
Thank you.
Cool.
But actually, it's not. It's all about appearances and perceptions and expectations. Okay?
Smoke and mirrors.
Then you got a topic.
See ya.
See you.
There you go. Cheers. So you got a topic for the second set. I think like a couple of years ago, I had a really considerable organizational change, and showed quite a book on the whole organizational change and how we get a lot of sort of practical things with the academic things together. Makes sense. And one of the things she said to me that one of the most important things in business is to manage expectations, and especially with IT. I think it's like it applies even more. Okay. So you're doing a PhD?
Yeah. Which was it last time?
Guys, just as you come in, grab one of each of those cards. All right, just grab a copy of one of those, please. You should hand it in the tube. It's probably easiest.
Because I just went to do it.
Yep.
I had no idea what was going on, but she said she'd.
No. You can give it to me now if you want.
I already gave it to her. She said.
To Sharon at reception.
Sharon.
Okay, I'll get it from her.
Okay, cool.
Just send me an email to remind me in case I forget. All right?
Yeah.
Thanks. Getting old now. Sorry? You can, but it's probably better to hand it in your tutorial. Yeah. So if you've got it lined up the tube, that'd be cool. Beautiful. handout. Did you grab a copy of those? Did you also use thermocletters? Good. Okay. No problems? Did you also use thermocletters? Sorry, playing the group. Make sure you use the software. You've got to email, you've got to register on the software. Thermocletters, it's a website giving information, and you send your Word document through to the electronic software as well as your hard copy. When you go to Democles' website, it'll have your auth tape number, and then you just follow the instructions there. Okay? Just grab a handout. Take one of each, yeah. Just grab a copy of the information you go past, please.